This video is about IR, or infrared spectroscopy, which is one of the ways we can use light to analyze organic compounds, and specifically we use IR to look at functional groups. So just a little background, what is light? And you've learned about light in other classes, and we're just going to do a brief summary. Light is electromagnetic radiation. It can be described as a wave or a particle. And when you look at light as a wave, it's made up of magnetic fields that are perpendicular to each other. And we can describe its wavelength and its frequency. The wavelength is the distance between the waves, and the units are distance, like meters or nanometers, and frequency are described as the cycles per second. The wavelength and the frequency are inversely related to each other, so when you multiply them together, it's the speed of light. So you can use the speed of light to determine the wavelength or the frequency if you know the other one. When you look at light as a particle, you can calculate the energy of one photon of this light, and it's equal to h, which is Planck's constant, time its frequency. So as the frequency increases, the energy of light increases. So frequency is a good way to talk about the energy of light. This is the full, what we call the electromagnetic spectrum, which describes increasing frequency is going to the left, and increasing wavelength is going to the right, so the energy is going up as we go left. Visible is sort of in the middle, so to the left of the visible are the energies, the light that are at higher energy. These are kind of the dangerous light, like X-rays and gamma rays and UV light are more energetic than visible light. Light that's to the right of the visible are the light that is less energy than visible. So these are the low energy lights, like microwave. Radio is over here, but it's not on this chart. And then infrared, there's the near infrared, and then the infrared that we're talking about is here. So it's not very high energy, and that's actually important. So when you shine infrared light on an organic compound, it doesn't have enough energy to break bonds. Up here, UV light and X-rays, they can break carbon-carbon bonds, they can break organic bonds, but UV light cannot. So what does it do when you shine UV light on organic compounds? It causes the bonds to, we say that they bend and stretch. So it puts energy in the bonds, and it causes vibrations, and those can be stretching. Think of it like a spring, like two atoms connected together with a spring. That's like a model for a bond. It also can make them bend, and then you can get like what are called in-plane bending vibrations and out-of-plane bending vibrations. And all of these things show up on what we call the IR spectrum. And what it does is specific functional groups have bonds that give very specific bending and stretching motions at specific infrared frequencies, or what we call wave numbers. So again, the energy is not high enough to break the bonds, even if the bonds are weak. And this is good for identifying functional groups. That's what IR is really good for. The functional groups that are easiest to identify with IR are pi bonds, and these can be carbon-carbon pi bonds or alkynes, triple bonds, CO double bonds, which are called carbonyls, and also bonds that can make hydrogen bonds, like OHs and NHs. These are the ones that are most useful to identify with an IR. So here's a typical IR structure. The stretches or the peaks, they start at the top and come down. I don't know why, they just do. And this is the intensity. And then The scale that's used along the bottom is called wave number, which specifically is frequency divided by the speed of light, and that's probably used because it gives the numbers, they're really easy to use. It goes from 400 on the far right, that's the lowest energy, up to 4,000 on the far left. So the energy goes up as we go this way, up, going to the left. The signals have the characteristics, three things that we'll talk about, which are wave number, intensity, and shape. Wave number is where does it fall along the scale here, like where does it come, that actually is the most important thing. Intensity is how long is the peak. If it's an intense peak, it's really long, it's almost to the bottom. If it's not an intense peak, it's shorter. And then what's the shape like? Some peaks are sharp, like this, and some peaks are broad, like this one here, where it broadens out. So wave number is where does it fall along the scale, and the most useful way to think about an IR is the peaks that fall on the left-hand side, which are the higher energy peaks. These are more useful, and these include bonds to hydrogen, like carbon to hydrogen or oxygen to hydrogen. Triple bonds fall around 2,000, around 2,200 or so, and then double bonds fall around 1,700 or 1,800 in that region. On the right, lots of peaks come on the right, but they're not very useful because this is where the carbon-carbon bonds come, and everything has a carbon-carbon bond. So there's a huge number of peaks in this region. So we call this the fingerprint region. It's just not a very useful region. So again, the diagnostic region, the left-hand side is often called the diagnostic region. It's more useful. The right-hand side is called the fingerprint region. It's in general not as useful. So let's look at what IR is good for. And if we have two compounds and we have each of their IR spectrum, one of them is an alcohol and this one is also an alcohol. So both of them are going to have the same characteristic alcohol peak. So we can see that peak here. It's the big broad peak that comes around 3,000 or so. And we see that both of these compounds have an OH peak. So what IR is good for is determining if a functional group is present in a compound. So if we take this compound and we measure its IR spectra, we say, oh, we know that this has an alcohol. But if we have the second compound and we measure its IR spectra, we say, oh, it has an alcohol also. What we cannot do is tell the difference between these two compounds by looking at their IR because they both look really similar. We can't tell the difference between one alcohol and another alcohol compound using IR. Not usually, anyway. So it's not useful for determining between compounds that have the same functional group. So the second thing is intensity, and that is the peak, long or short. The stronger the vibrations, the longer the peak. The shorter the vibrations, the shorter the peak. So both of these are pi bonds, but if you have a carbon-oxygen pi bond, it's more polar. So it has a stronger vibration because of its polarity. So it's going to give us a stronger peak. And the IR peak in the IR is going to go almost all the way down to the bottom. And that's, we say, a very intense peak or a strong peak, and that would be indicative of a C double bond O, a carbonyl. And a carbon-carbon double bond is also there, but it's definitely going to be shorter because it's not polar. Just as an aside, the IR is typically really useful for identifying carbonyl compounds. It's usually one of the first things that you look for in an IR. Easy to spot. It's very big, and it comes in a really specific place. This is just a recap. Strong vibrations and weaker vibrations. Okay, the third thing is the shape, and is a peak broad? Is it look poofy kind of? Or is it sharp and narrow? And that has to do with, usually it has to do with hydrogen bonding. So bonds that can make hydrogen bonds, it makes them a little bit variable is one way to think about it, which broadens the peak. And if they can't hydrogen bond, it tends to be more narrow. So OH peaks are the ones that really typically look like this. So here's an example of two compounds. The first one is 2-butanol, so it has 4 carbons and it has a hydroxy group at carbon 2, so 2-butanol. And we see that it has an OH peak here. If it has free OH that's not hydrogen bonding, it will show up in the same region, but it'll be sharp. I will say that OH peaks are usually broad like this one. They're not usually sharp. The second compound here is butyric acid, which is a carboxylic acid that has 4 carbons. And we see that a carboxylic acid is going to have a C double bond O, which is the carbonyl, and that comes here, and that's really long and strong, sharp. And then it also has an OH group. So this kind of overlays everything else, but it has a big OH. We call this an OH stretch. Okay, so there's some practice for you to do in Schoology. There's 3 quizzes. I divided them up. They're straight out of the notes, so if you want to work through them on the notes and then go into Schoology to check your results, it'll be, for these pictures, you're choosing between, is it an alcohol or a carboxylic acid, or is it neither? Those are your 3 choices. So for these 6 IR spectra, you're not trying to figure out what the compound is. You're just looking for functional groups here. And that's the IR quiz number 1. Okay, the last thing I want to talk about is amines. And H peaks specifically. 2 types of amines show up in the IR spectrum. One is a primary amine, which means it's a nitrogen that has 1 carbon group and then 2 hydrogens. So because it has 2 hydrogens, it's going to have 2 signals in the IR because the 2 NH bonds. If it's a secondary amine, it has 2 carbon groups, that's what makes it secondary, and 1 hydrogen. And this compound will have 1 NH signal in the IR. So there's some examples of that coming up. Just as a note, tertiary amines, which are amines that have no hydrogens, they have 3 carbon groups. They cannot be detected in the IR because there's no NH peak to look for. So here's examples. Here's a primary amine. It has the 2 NH bonds. And in this region, they're a little bit broad, not so broad. They are really short because they're weaker than the OH bonds. And you see that there's 2 of them. If it's a secondary amine, it has just the 1 peak because it has the 1 NH. They both come around 3300, which this is the CH. These are the CH stretches, which pretty much every organic compound is going to have a big CH stretch around 3000. Just to the left of that is where we look for OHs and NHs. OHs would be really big and broad, like a big bucket, and NHs are smaller, and you can tell if it's primary or secondary, again, by if there's 2 little blips or one little peak. They are, to be honest, you'll see later, they are not always this easy to spot. Okay, second piece of practice is the Schoology quiz number 2, in which you're going to look at these 6 pictures and decide what functional group is present. Does it have a ketone? That would mean it has a carbonyl. Is it an alcohol? Is it a carboxylic acid, which would have a carbonyl and an alcohol? Or is it a primary amine, or is it a secondary amine? All of these IR spectrum are going to be one of these 5 choices. And that's IR quiz number 2. And again, just go in and do it on your own and check. I think you could do it a few times and it'll average your score. So, okay, one more practice quiz. These are getting progressively a little bit harder as we go. This again has six IR pictures, and with that you're going to try to match. There's 6 possible structures, and each one of these structures is in one of these pictures. So you're trying to like basically match them. And again, this is in Schoology. It's IR quiz number 3, and it has all the pictures in there, so you don't have to leave your notes open. But you can work it out on paper before you try it there, if you would like to. So here's a summary. So keep this handy when you're doing the quizzes or looking at IRs in general. You're not expected to memorize this. At least I was never expected to memorize this. Like when I took class, we always had access to a chart. Some charts are better than others, I'm not going to lie, and this one's okay. But this gives you a general feeling for where the peaks come. What it doesn't tell you is, are they strong or weak or broad or sharp? You're going to have to practice enough that you are familiar with that. These are the useful ones. This is, what table is this? Table 13.2. This is a really useful chart. I would keep this handy. The next page is another chart. Just a note. These are all carbonyls, and depending on how good your IR is and how good your chart is, you can often tell the difference between like an ester versus a carboxylic acid versus an aldehyde or a ketone based on where the IR stretch comes. You can't always do that, but sometimes you can. This is another chart. These are not so useful. Like carbon, oxygen, where do they come? These tend to come on the right side in the fingerprint region. Unless you know exactly what you're looking for, you can't always. These are just in general not so useful.